I'm really glad to attend the WSDM-23 and share our work. Our paper title is Minimal Entropy Principle Guided Graph Neural Networks. And here is the author list. Let's move to the outline. We have divided today's slides into 6 parts. The first part is background. Firstly, I would like to indicate the general mechanism of graph neural networks because our work is based on GNN. GNN are always dealt with node level or graph level tasks. For node level tasks, such as node classification, GNN generate node embeddings for each node in the graph to classify them. For example, in this graph, GNN generates embeddings for nodes V1 to V6 and predict the label of each of them. And for graph level tasks, GNN generates graph embedding for each graph and predict their labels. The same thing of these two tasks is that GNN need to generate embeddings, but how to determine a suitable dimension D for the generated embedding is still an issue. The second part is about motivations and aims. Let's take a view of current method to find the suitable dimension for GNN. Researchers always use the greedy search-based method. Such method pass a GNN multiple times and choose the dimension as the highest accuracy. With the highest accuracy. For example, we pass a GNN 7 times on the 7 different dimensions. Because the GNN has the best performance on the dimension 50, we regard the 50 is the suitable one. But such method has fatal drawbacks. When we need to pass a GNN multiple times, it means it's time-consuming and resource-consuming. And also, this method may not accurate when we set large search gaps. Thus, we want to develop a method can estimate the proper dimension without needing to pass a GNN. Another dimension-related problem of GNN is for graph-level task. In a set of graphs, there are different graphs in terms of size or structure. But current GNN always encodes them into a unified dimensional space, which ignores their differences. Thus, we hope to develop a method can encode them into diversity dimensional space. Before the start of our model, it's essential to get some preliminary knowledge. The first concept is minimal entropy principle. In briefly, when a graph entropy equals the minimal value, we can think this graph has the most stable state with the less uncertainty. Another concept is structure entropy, which is a metric for measuring the complexity of a graph's structure. In general, the more complex the graph, the larger the structure entropy. Turn to the methodology part. Our model has two methods. The first method is for GNN on node level tasks, which estimates the dimension for node embeddings, called NDE. This is an overview of the NDE. In briefly, the NDE counting both structure entropy and attribute entropy to estimate a function. Such function calculates the graph entropy on the different member of dimensions for node embeddings. Then the suitable node embedding can be regarded as while the graph entropy equals the minimal value 0. In this situation, we think the dimension can help this graph achieve a most stable state. In order to capture the structure information accurately, we develop a new structure entropy involving four steps. And these steps are highly related to GNN running process. The second method is for GNN on graph level tasks to estimate the graph embedding dimension called NDE. This method is a new training architecture for GNN to encode graphs into diversity dimensional space. In a let's take a simple example. In a graph dataset, we have 4 graphs. And firstly, we use NDE to detect the suitable node embedding dimensions of each of them as D1 to D4. Since most GNN shares a dimensional space between node embedding and graph embedding, we can also think D1 is available for encode the graph 1 for the graph embedding. Then we use the k-means algorithm to cluster D1 to D4 and assign each of them a closed k-means central. In this example, D1 and D2 are assigned to central C1, and D3, D4 are assigned to the central C2. C1 and C2 will be the candidate site to encode these 4 graphs. Because D1 and D2 are assigned to the central C1, so in the final, we will encode the graph 1 and graph 2 into the C1 dimensional graph embedding space. And also, D3, D4 are nearest the C2. We encode graph 3 and graph 4 into C2 dimensional space. Thus, the GDE create a new assignment mechanism, assign each graph a customized dimension. And in other words, GDE encode this graph into diversity dimensional space. The last second part is experiments. We conduct a comprehensive experiment to verify the effectiveness of GDE and NDE. Let's take a look of this table. The GDE has improved the GNN performance for graph classification tasks on 4 datasets, enzymes, D&D, proteins, and collab, and beats the grid search-based method. And also on node level tasks, NDE is also available, such as for semi-supervised node classification on undirected graphs. The our model beats the greedy search-based method and another method for estimating the node embedding. And for the semi-supervised node classification on directed graphs, there is only our model can estimate the node embeddings on directed graphs. So we set the gradient search-based method as the baseline. We also achieve superior performance. And also it works on unsupervised network embedding. Move to the time efficiency analysis. Move your eyes to this table. For the collab data size, it has 5,000 graphs. Our model only need 1,347 seconds to detect the suitable dimension for this data set. But without our model, we need to pass a GNN multiple times, and each time we need running over 10,000 seconds. So our model saves a lot of time. And the last part is conclusion. In conclusion, we propose a novel embedding dimension estimation framework called MGDE, which has 2 methods, NDE and GDE. NDE estimates the suitable dimension for node embeddings, and GDE works for graph level embeddings. For graph level tasks, MGDE proposes a new assignment mechanism that assigns each graph embedding with a customized member of dimension instead of a unified one. Extensive experiments demonstrate the effectiveness of MGDE in guiding GNNs on both node and graph level tasks. That's all of my presentation. Thanks for your listening and attention.